Hey everyone, and welcome back to this class, Artificial Intelligence, Reinforcement Learning in Python. In this lecture, I'm going to introduce you to value functions and the Bellman equation. A lot of people have been requesting this since the math for the Bellman equation can be a little hard if your probability skills are not yet where they need to be. So in this lecture, we're going to go over a very intuitive, graphical explanation of the Bellman equation and hopefully reintroduce you to some important probability concepts that you'll need for the rest of this course. So I think the most important concept by far for understanding Bellman is the idea of the expected value. The expected value is a strange concept to a lot of people. Let me explain why. Suppose I have a coin that gives me heads or tails. You can think of this as win or lose. Importantly, we encode these numerically as 1 and 0. So heads you win, you get a reward of 1. Tails you lose, you get a reward of 0. Now suppose the probability of winning is 60%. The expected value is therefore 0.6 times 1 plus 0.4 times 0, which is 0.6. Why is this weird? Well, the expected value is actually a value you can never expect to get. Wrap your head around that. The expected value is a value you can never expect. So what's the point of expected values then? Well, the expected value of a random variable tells us its mean, or in other words, the average. So if I gather up all the heights of the students in my class and I calculate the average, perhaps no student actually has that average height, but it's a useful statistic. Similarly, it doesn't matter if I can never get 0.6 from a coin flip. It's an average. It tells me if I flip this coin 1,000 times, what I should get on average. One useful way to think of probabilities and expected values is a probability tree. I draw a circle to represent where I am now, and then I have branches to the possible places where I can end up, and I write the probabilities along the edges. So I can see that I have a 40% chance of going to the left and getting 0 reward. I have a 60% chance of going to the right and getting a reward of 1. My expected reward then is the weighted sum of all those rewards, where the weights are just the probabilities of each branch. And by the way, this extends to any possible number of branches, so it's not necessarily a binary coin flip. So pretend we have 5 events. The method of calculating the expected value is the same. It's equal to probability of event 1 times value of event 1 plus probability of event 2 times value of event 2, all the way up to probability of event 5 times value of event 5. In general, we can say it's the sum over all possible events of probability of event times the value of the event. This is the exact definition of expected value. To use more precise mathematical notation, we say that if big X is a random variable, then the expected value of X is just the sum over all possible values of X of P of X times X. So why are averages so important? Consider again the game of tic-tac-toe. Realistically, I can't predict what my opponent is going to do next. My opponent can do any number of things. Sometimes I might end up winning. Sometimes I might end up losing. Each time I will get a different total reward. Again, we can use a tree to represent this idea. The only difference is this tree is much larger and has more than one level. You may also recall from your previous studies that trees are recursive. So if I take a tree and I look down at one of the children of a root, this is also called a tree. In other words, the child of any node in the tree is the root of another tree. This idea of recursiveness will become important later on. Now every time we play this game, we're going to take a different path down the tree. Each path has a different probability, but just like the simple tree we saw earlier, we can still have this concept of what's the weighted sum of total rewards I get with this tree with these states and these probabilities. And so the value of this state is precisely the average reward I will accumulate in the future by being in this state now. Not the exact reward, because that can be different every time, but the average, or in other words, what I would get on average if I went this way many times. So let's break down these concepts and summarize what we know so far. We know that at each state S, I'm going to get a reward R. We know that my overall return G is the sum of all rewards I get. But we also know that games are random. So if I start here today, and I start in the same place tomorrow, the total return I get today might be different than the total return I get tomorrow. Therefore, we need some way to represent the average of these returns, or in other words, the expected value of the total future return, given that I start in state S. So this combines two notations. The vertical line means given, so we are assuming that the fact that I'm in state S is true. If we're given something, that means it's not random, and there are no probabilities associated with it. To the left of the given symbol are the random variables, in this case just G. So we're saying we know that G can be random, but what's the average given S? This is called a conditional expectation. The next concept we're going to discuss is one of the most fundamental concepts in reinforcement learning. It's central to just about every reinforcement learning algorithm we're going to study. The idea is this. I know that every game is going to consist of a series of states and rewards. Let's pretend for a moment that everything is deterministic, so the reward we would get is the only reward we can possibly get at any state. This lets us drop the expected value symbol for now. As you may recall, the expected value of a value that's not random is just the value itself. So for example, the expected value of 3 is just 3. So we are excluding any expected value symbols here for simplicity. Then we can just call our states and rewards S1R1, S2R2, and so on up to SNRN. So because the value of a state is just the sum of all future rewards, we can say that V of S1 is equal to R2 plus R3 plus R4 all the way up to Rn. The value function for S2 is V of S2 equals R3 plus R4 plus R5 all the way up to Rn. But now we can see a special relationship between the values of successive states. In particular, I can plug in V of S2 into the expression for V of S1. We get V of S1 equals R2 plus V of S2. In other words, this is a recursive equation. Of course, if you wanted to discount future rewards, we can do that too without any significant changes. So we say V of S1 is R2 plus gamma times R3 plus gamma squared times R4 and so on. So recall that gamma just lets us discount the future if we assume that the present matters more because the future may be unpredictable. So this recursiveness is going to be a very important theme in this course. We know that this value function is going to be an expected value, and we know from our tic-tac-toe example that our job is to estimate this value. But we can see how it has this sort of recursive structure. The value at this state is an estimate, and it depends on the value at some other state, which is also an estimate. So it's an estimate which itself depends on an estimate. This course is, generally speaking, about methods for optimizing this array of estimates, which depend on each other, all at the same time. So what can we do now that we have this relationship between the value at state S and the value at state S prime? Notice how I've replaced S1 and S2 with S and S prime just to be more general. I'm also calling the reward just R by itself, but sometimes this is also denoted as R of SS prime to show that it's the reward we get for going from state S to S prime. In any case, recall that we started this lecture by noting that the rewards and state transitions can all be probabilistic. So in order to denote that, we just put this expected value symbol back on our equation. This is the essence of the Bellman equation. Since we can express V of S prime also as an expected value, we can even do something like this where we expand this out. So what we've done here is basically expanded the recursion. Note that this is just for visual purposes and we won't actually do this in any of the algorithms. Now, since this is meant to be an easy introduction lecture, I'm not giving you all the mathematical details, but if you're interested, that's what the next lecture is for. It's going to be much more rigorous, so in general, I would consider it to be optional. Understanding this lecture is enough to understand the rest of this course. Now, for simplicity's sake, I've dropped the conditional part of the expectation, among other things, so you could put this back and write the equation as the same thing but given s on the right side. But this is not crucial to your understanding of this concept. One useful extension of the value function v, which depends on s, is another value function q, which not only depends on the state s, but the action a. We call v the state value function and we call q the action value function. The reason why we need both will be discussed in a future lecture, but for now let's just talk about what they are. So v of s tells us, what is my expected future return given that I'm now in state s? Similarly, q of sa tells us what is my expected future return given that I'm now in state s and I do action a. So it's a way of incorporating more data into the prediction and to provide more granularity. What this means is that since v doesn't depend on a, it must somehow take it into account. We just don't know how yet. Save this thought because we'll be discussing it in a future lecture. We will touch on how v and q are related, but for that we need to incorporate the idea of policies, or in other words, the thing that tells us what action to do given the state we're in.